And the next talk in our section is the talk of Professor Reinfelds.
Decoupling of quasilinear dynamic systems. There is outline and some introduction. The reduction principle in the theory of stability for systems of autonomous differential equations first time was proved by Bliss, and after them many mathematicians extend these results, and beginning with Hartmann and Grobman, and many mathematicians work in this field. In the present talk, we will generalize reduction principle to the case of dynamic systems on time scale in Banach space, whose linear parts split into two parts and satisfy weaker conditions than exponential dichotomy, and use standard technique for local modifications of reduction theorem are obtainable. First I will give some short introduction to time scales. It is new direction, and it begins with this German mathematician Stefan Hilger, and he introduced the calculus of time scale in order to unify continuous and discrete analysis. And here I will give some basic definitions shortly. Definition, what is time scale? It is arbitrary, non-empty, closed subset. Non-empty closed subset of the real numbers R. No examples. Practically real examples are real numbers, integers, natural numbers, union of closed intervals, quantum calculus, and Cantor sets are also time scales, as you yes. But the examples of no time scales, the rational numbers, the irrational numbers, the complex number, the open intervals are not time scales. It is a difference between what is time scale and what is not time scale. And we denote time scale with symbol T, first letter. And so let us start with defining the forward and backward jump operators. The forward jump operator is defined by following equality is infimum for of all S, which S is greater than T. And backward jump operator is defined as supremum from all S, then S is less than T, rho T. And also important thing is Green's function, which is defined by this equality, the difference between forward jump operator and identity operator. Now, for example, what is time scales, what we usually consider. If T is R, it is time scale. We have this forward operator sigma T is equal T, rho T is also T, every point is dense, and the Green's function mu of T is 0. So this is for time scale is real numbers. If it's integers, then sigma T is T plus 1, rho T is T minus 1, and the Green's function is constant and equal 1. So, as I said, this is unification of discrete and continuous calculus. So we need define what is derivative. Derivative is function. We define derivative at the point. And let us have function, and derivative is a number with the properties that given any epsilon, there is neighborhood U, of such that difference f sigma t minus fs minus f delta t sigma ts is less than epsilon. No, it is, as you understand, this is something like a traditional definition of derivative. And we call this derivative the delta derivative. And again, explain what means in the two main cases when it's R and Z. If the time scale is R, the delta derivative f is delta differentiable if exists such limit. And it means that f is differentiable in the ordinary sense of t. And in this case, we have no ordinary derivative. If t is z, then a function is delta differentiable. It follows from definitions that f of delta t is ft plus 1 minus ft is usual forward difference operator, and every function defined on z is differentiable. So then really important thing is function at the continuous function. It means the function is continuous at right-hand points, and its left-sided limits exist at all left-hand side points. No, if f is continuous usually, then of course f is Rd continuous. Any f from integers are Rd continuous, and we denoted this set of function by CR. Then integral. A function is called antiderivative. No usual definition that f delta t is ft holds for all t. And it proves a theorem that every continuous function has antiderivative, in particular, then f defined by such integral is antiderivative. So, and theorem, what means for traditional cases, if t is r, and that the integral is to the right, this timescale calculus is usual Riemann integral. But ft is z, that integral is such so. If you wanted to study deeper, then you can use, for example, book of Warner about time scales. Here I mentioned only the main definitions and yes. So let us start with our main object about dynamical systems. X and Y are one-ax spaces, Lx and Ly are one-ax spaces of linear bounded endomorphisms. T is unbounded above and below time scales. At the beginning, we consider the case T is unbounded above and below time scales, and the next part of my talk only when T is unbounded above time scale. So consider the following dynamic systems. One, and its linear part 2. And we propose that these all functions are continuous and regressive, and we will do additional conditions. So what means regressive? The map is called regressive with respect to t provided identity plus mu dat is invertible for all t. I remember in case of R, mu of t is 0, and so it's all are regressive. But in the case of a discrete case, of course, it depends on mu of t regressive. And what I will say about nonlinear parts, and that the nonlinear parts satisfy Lipschitz conditions with some epsilon, uniform Lipschitz conditions with some epsilon. And we propose that we have equivalent point as 0, y0. And here I denote solutions of this dynamical system by P, P, P. So what I will say about linear part, X and Y are transition operators of the linear dynamical systems on time scale. As you remember, this was this system 2. And this was nonlinear system 1. And we propose such conditions of separations that integrals, maximum of 2 integrals, this magnitude is nu is bounded, and we call this magnitude by constant of separation. What it means in classical cases, what means this condition of separation? If T is R, A and B is constant operators, or so, that reduces that nu is such integrals, and these integrals converge if the spectrum of the map B is located to the left of the spectrum of the map A. What it means is that exists a bounded constant of separation. And the spectra are separated by the vertical line in the complex line. Now, here is for an autonomous case. The first, the whole result, but in new time scales is theorem of Lipschitz invariant manifolds. Let for epsilon nu is less than 1. It is very important condition for our results. Epsilon is this from Lipschitz constants, and nu is as I said, constant of separation. And if this magnitude is less than 1, then exists 2 mappings, 2 invariant manifolds, U and B, and P is a condition of invariance, Lipschitz conditions, and some condition of tending this solution to this invariant manifolds. And analog is analog for V. Here I propose that system 1 and 2 are regressive. But if the system is not regressive, then it is possible to prove only these 3 conditions. So, and the proof is based on principles, contraction principles. We use such set of functions in there, and this is one of space, and we take the closed subset of this one of space where the function is bounded and satisfy Lipschitz conditions, and analogs for V. And then we assume such a number P, and here we prove that this number is less than 1, and it is less than 1 when this difference is positive. And of course, there are another thing. We know that linear system is regressive. Irrational system also is regressive. But our simplification, it is not clear why this system will be regressive. But also using the properties of integrals, it follows the dynamic system on time scales. We see system 3, and U is from this M1, then this system is regressive, has regressive right hand. And analogously for the other part, for other simplifications. So here is the idea of proving these invariant manifolds, use functional equations, and we get, here I know these solutions of these differential equations, and we use this, and we consider or reduce dynamical system. Here, if we look at system 1, there was instead of u, y, and instead of v, x. But as you see, the system 5 splits into 2 parts. The first of them does not contain the variable y, and while the second one is independent of x. So, of course, this system 5 is simpler than the initial system. And the main thing is that this first part is independent of x. It does not contain y, and the second part does not contain x. So what is a definition of dynamical equivalent? Two systems of dynamical equivalent are equivalent if their XX map hash. He forfeits T is homomorphism. He fulfills the condition of conjugacy, and we need for non-autonomous case additional condition. If we have ordinary autonomous system for differential equation, it is need to fulfill condition 1 and 2. But for an autonomous way, a need additional condition. It may be different. In our case, we have such condition that the difference between hash and identity is such estimate. And the proof consists, the limit theorem, let for epsilon v is less than 1, and the linear system is regressive, then the dynamical systems 1 and 2, 5 are on time scales are global dynamical. As you see, simple condition. So, but the proof is very long and consists of several steps. The steps are here. Here are 10. And the first step is the following. We consider such Banach space, and I would like to just mention, then in definition, we use this function u, that was found in the first theorem, and construct the functional equation, And using these all conditions, it is possible to prove there exists unique solution of this functional equation, K1. And for step 2 is something analogous, and here we used the V in definition of Banach space, and also have a unique solution of the functional equation. And we may define the mapping H1 by the equality. H1 is identity plus K1 and L1 divided plus L1, where K1 and L1 is defined in first and two step, and fulfills condition of conjugation. But more complicated case is to prove that this H1 for fixed T is as inverse, and the composition is that this H1 is homomorphism. And for proving this fact, we need a long proof which consists of 8 steps. In the first 3 and 4 steps, we define new spaces, as you I mentioned in definition of the space used, maps obtained in previous steps, as you see, K2 functional equations, and occasionally we find H2 that in such more complicated case that this satisfies conditions of conjugation. So we have H1 and inverse H2, and then we need to prove that composition of H1, H2, and H1 is identity. And for this we need several steps. I here mentioned only the basic facts that you, in definitions used, maps obtained in previous steps, more complicated functional equations, and more technical work, and occasionally step 7, 6, 7, 8, 9, 8. Occasionally we get in first and seventh step we have that H1, H2, this is identity map, and 8, 9, 10, then we prove this H2, H1 is identity. So it is proved this theorem, and this initial system can be decoupled in simpler view. The homomorphism established in the chromotypical events, 1 and 4. Thus the proof of theorem is complete. I previously said that happens when the linear systems are not regressive. And suppose such case that only linear system, the part of this system too, is regressive. Then it is possible to prove the existence of such map K, and the system, initial system, is dynamically equivalent to such system. Of course, the first part does not contain Y, but the second part contains X, but in other form. So it is maybe some simpler, but not so good result that in the first theorem. And the proof is either It consists of 4 sets,
Что-то
two
завис.
using corresponding Banach spaces, functional equations, using our conditional theorem, and then occasionally we have that H2, H1 is an identity, and here I have that H1, there is changes only in this first part, and the second is only Y. And after 4 steps, and no idea is similar, general, but technical more complicated, and it is possible to prove such theorem. Thank you for your attention. Thanks.
Окей. Так, есть, да. Окей, thank you very much. What questions do you have?
Вопрос?
Да, какие вопросы? I have one question. When we solve, for example, the second order differential equations in time scale, how can we do it? What is the procedure? Because we can define one-dimensional integral, and if we would like to integrate the second order differential equation, what is the method?
I don't catch your question.
Я хотела спросить, каким методом мы интегрируем дифференциальные уравнения второго порядка, если мы вот знаем, как интегрировать один раз, да, вот как мы дальше понимаем решение уравнения второго порядка, скажем, и более высокого.
Ну, вообще уравнение можно всегда свести второго порядка первого порядка введением новой функции.
К системе мы имеем в виду.
Ну, систему тоже можно, да. Ну, конечно, здесь ограничение такое, что должно привести к системе такого вида, как уравнение 1, да. Если не приводится, ну, тогда нужно думать, что делать и как. Но вообще этот результат, это уже содержит полностью классическую теорему Гроумана-Хартмана и принцип редукции и так дальше. Я думаю, что свелось, ну, как формулировку к более простому виду, и эта оценка 4 эпсилон ню меньше единицы не улучшаемая. Если можно построить пример, если 4 эпсилон ню равно единице, тогда ничего не получится. Ну, не можно применить. Это существенно, что эта величина меньше единицы. Да? Вот, что действительно есть разделение, ну, какое-то разделение. Разделение зависит от этого константа разделения и, конечно, от эпсилон. Но если эпсилон очень маленький, тогда это получается. Если эпсилон увеличить, тогда, ну, понятно, ничего не получится. Ну, по крайней мере, эта теорема не будет верна.
Понятно. Thank you very much. Other questions? Okay, let's thank our speaker. Andrei, thank you very much.